Good morning, everybody. Today we're going to talk about how to do a Lewis dot structure for different molecules. I picked several molecules from your assignment. We're going to start out with phosphorus chloride. You guys are going to learn how to name those later on. Whenever you have a molecule and there's a particular atom where we only have one of that atom, you put that in the middle. So I put phosphorus here, and I drew the Lewis dot structure for phosphorus. When we look on our periodic table, we can see that phosphorus has 5 valence electrons, so that's what I drew. Then I drew chlorine. Now chlorine is a halogen, so we know that it has 7 valence electrons. It desperately wants 8. Phosphorus has 5. It also wants 8. So they're going to come together in a way that everybody can share electrons and everybody can be happy. Chlorine and phosphorus decide to share 2 electrons each. You can think of it as this. Chlorine has an electron there. Phosphorus has an electron there. This chlorine is now touching 8 electrons, and so that makes it happy. This phosphorus now gets to share one of chlorine's electrons, and so that makes the phosphorus a little bit happy. Not completely, but a little bit. You can either draw the 2 electrons, but that starts to become really complicated when we have big molecules. So something that we often do instead is we just draw a line. That line represents 2 electrons being held together in a bond. Well, the chlorine is happy, but the phosphorus isn't. Also, we know that we need 3 chlorines. So we're going to add in 2 more chlorines, and each of them is going to do the same thing. Another chlorine is going to come here and share, and then our last chlorine is going to come over here and share. It doesn't really matter where you put them. I could have put one of these up here and left the right side blank, but I'm short, so I don't like to use things up at the top of the board very often. I'm going to go through and just erase these middle electrons and just replace those with those lines to represent the bonds. So now, if we look, phosphorus has 2, 4, 6, 8 electrons that it's touching. Remember, each line is 2 electrons. And each of the chlorines is also touching 8 electrons. So everybody's happy. And we've completed our Lewis dot structure. Now we're going to come down to calcium oxide. When you were filling out your worksheet, you discovered that calcium and oxygen have a very high electronegativity difference. And you wrote down that this was an ionic bond. That means one of these elements is going to completely steal the electrons, the other one is going to completely donate the electrons. So, calcium is one of our alkaline earth metals. We know that it wants to get rid of those 2 electrons. Those 2 electrons are going to come over here to oxygen. So calcium becomes fully positive with a charge of +2. And oxygen becomes fully negative with a charge of -2. Let's come back up here to our phosphorus chloride for just a moment. Nothing stole electrons, so nothing became wholly negative. And the phosphorus certainly didn't donate any electrons, so it didn't become fully positive. But the chlorines have a very high electronegativity. They're going to pull very strongly on the electrons. The electrons are going to spend a little more time a little bit closer to each of the chlorines. So whichever side of your molecule has more chlorines, that side ends up just a little bit more negative. This side up here with the phosphorus, where there are no chlorines, that side ends up just a little bit more positive. We don't want to write a positive and a negative. That makes it look like something has completely donated or completely stolen. So instead, we put a sigma there, and that just indicates that this is a polar molecule. This side is a little more negative, this side is a little more positive, but it's not completely separated like in the ionic bonds. Let's go ahead and write down that this one is polar covalent. Okay, let's move on to another one. O2. We have 2 oxygens. Well, as we look at this, we can see that each oxygen has 6 electrons. Each oxygen wants 8. So we can start out by just putting that one bond, like we've been doing, and that helps. Each oxygen is now touching 7 electrons. It's a little bit happier, but they're not completely happy. We can't add something else in. We only have these two oxygen atoms to work with. So what happens is these two electrons over here come into the middle and form another bond. O2 has what we call a double bond. Now, each oxygen is touching 2, 4, 6, 8 electrons. And so each oxygen is happy. This ends up being a non-polar covalent bond. Each oxygen is exactly as electronegative as the other, so neither side becomes positive or negative. Let's come down to another one that also has something more than just single bonds, and this is hydrogen cyanide. So, hydrogen, carbon, and nitrogen. When you have something like this, whenever carbon is involved, I usually put carbon in the middle. That's the one that usually likes to make the most bonds. So that's an easy one to start in the middle and branch all of your other atoms out from it. Hydrogen wants to share a bond with carbon, so they will share those 2 electrons. We have 1 bond. That's great. Carbon and nitrogen will share a bond. That's great. But now you can see that carbon still wants to make 2 more bonds. And if we look over here at our nitrogen, the nitrogen still wants to make 2 more bonds. So carbon and nitrogen form a triple bond. So now let's count the number of electrons that everything is touching. Hydrogen has 2 electrons, it's happy. Carbon is touching 2, 4, 6, 8 electrons. It's happy. Nitrogen is touching 2, 4, 6, 8 electrons. Nitrogen is happy. The entire point of atoms coming together to form bonds is to fill up their valence layer. They're going to continue doing whatever they have to do in order to have 8 valence electrons in their outer layer. The only difference, of course, is going to be hydrogen. Hydrogen is happy with 2. I hope that helps you.